On the morning of April 14th, 2025, a magnitude 5.7 earthquake struck Silver Springs, Nevada. The ground shook hard enough to crack walls, knock items off shelves, and send people running into the streets of a small town that does not have many streets to run into. It was the largest earthquake in western Nevada in years. It made the news for 2 days. 14 days later, a magnitude 4.7 struck the Pahranagat shear zone, roughly 400 kilometers to the southeast. It rattled chandeliers in Las Vegas, high-rises 95 kilometers away, and disappeared from the news cycle before the day was out. 10 days after that, smaller events began clustering along fault structures in the region between the two ruptures. Not large enough individually to make headlines, but collectively tracing a pattern in the seismicity catalog that seismologists recognize. A pattern that has a direction. A pattern that, if it continues, points toward one of the fastest-growing cities in the United States. 2.5 million people live in the Las Vegas metropolitan area. Most of them have never thought seriously about earthquake risk. Nevada is not California. The San Andreas is not here. The mental model most residents carry, that serious earthquake danger is someone else's problem located somewhere else on a fault with a famous name, is not unreasonable, given what they have been told. It is also incomplete in ways that the April 2025 sequence is beginning to make visible. This is the story of a fault network doing something that fault networks in this region have done before, and the last time they did it, the sequence did not stop until it had expressed itself at every structurally connected segment it could reach. To understand what is happening now, you have to understand the architecture of what is underneath Nevada. Most people know about the San Andreas Fault. That is by design. It is large, it is dramatic, it runs through some of the most populated real estate in North America, and it has a body count that makes it impossible to ignore. What most people do not know is that the San Andreas handles only about 3/4 of the relative motion between the Pacific Plate and the North American Plate. The remaining quarter does not simply disappear. It is absorbed by a broad, distributed zone of faulting that extends from southeastern California across the Mojave Desert, across most of Nevada, and northward into Oregon and Idaho. This zone does not have a single famous fault running through its center. It has hundreds of faults, some named, some mapped, but unnamed, some not yet mapped at all, each absorbing a fraction of the strain being delivered by the plate boundary, each accumulating stress at its own rate, each connected to its neighbors through the stress field of the crust in ways that are only partly understood. Geophysicists call this the Walker Lane and Eastern California shear zone system. Together, they accommodate somewhere between 10 and 20 millimeters of crustal motion per year. Modest by San Andreas standards, but enormous in absolute terms when you consider how long it has been accumulating and how many people now live within its footprint. The Walker Lane runs roughly north-northwest through western Nevada. The Eastern California shear zone runs through the Mojave Desert to the south. Between them, at the structural junction where strain transfers from one arm of the system to the other, sits the Pahranagat shear zone, a distributed fault complex in Lincoln County, Nevada, that the USGS has formally identified as one of the principal earthquake-producing structures in the entire southern Great Basin. The April 14th Silver Springs magnitude, 5.7, was a Walker Lane event. The April 29th Pahranagat magnitude, 4.7, was a southern transfer event. The direction of travel in this sequence, north to south from Walker Lane toward the structural relay, toward the Eastern California shear zone, toward the Mojave, toward the urban corridor that terminates at Las Vegas, is not an accident of geography. It is the geometry of how stress moves through this particular network. It has moved this way before. The historical record of western Nevada seismicity is not widely known outside the geophysics community, but it is one of the most instructive sequences in the entire catalog of continental earthquake science. Between 1915 and 1954, the Central Nevada Seismic Belt, a roughly linear zone of fault systems running north-northwest through the state, produced 4 major earthquakes in sequence. The 1915 Pleasant Valley magnitude, 7.3, the 1932 Cedar Mountain magnitude, 7.2, the 1954 Dixie Valley and Fairview Peak events, both in the magnitude 7 range, rupturing adjacent segments within minutes of each other on the same afternoon. 4 major earthquakes, 4 decades. Each one approximately the next segment of the same regional system. Each one redistributing stress into the surrounding crust, advancing the loading on adjacent structures, moving connected fault segments closer to their own failure thresholds. Nobody connected them into a sequence while the sequence was happening. The 1915 earthquake was documented. The 1932 event was documented. The 1954 events were documented. But the framing was always individual events, this fault, this time, this magnitude, rather than a network expressing itself progressively across time and space. The sequence only became legible as a sequence in retrospect when researchers with the full catalog in front of them could see the spatial and temporal pattern that the individual events had traced. That is the problem with network behavior in distributed fault systems. It looks like isolated events until it does not. And by the time the pattern becomes obvious to everyone, some portion of the sequence has already occurred. The April 2025 pattern is not the central Nevada seismic belt. The faults are different, the magnitudes are smaller, the geometry is not identical, but the structural logic is the same. A linked system of fault zones in the diffuse plate boundary with stress moving through the network from a northern source toward a southern relay, in a region where the relay connects to a fault corridor that terminates in a major urban area. Las Vegas did not exist during the central Nevada seismic belt sequence. The population of the entire state of Nevada in 1915 was less than 80,000 people. Today, the Las Vegas metropolitan area alone contains more than 2.5 million. The question of what this region's fault network is doing matters in a way that it did not matter during the era when these sequences were first documented, because the people at the end of the stress pathway are no longer hypothetical. Understanding how the stress is moving requires understanding the physical mechanism. When a fault ruptures, it does not simply release energy at the epicenter and leave the surrounding crust unchanged. The deformation of the rocks during the rupture permanently redistributes stress throughout the surrounding region, instantaneously for static stress changes and progressively over days to months for post-seismic adjustments driven by fluid migration and viscoelastic relaxation of the lower crust. For some faults in the vicinity of a rupture, this redistribution moves them closer to failure, increases what geophysicists call the Coulomb failure stress on those faults. For others, it moves them away from failure. Whether a specific fault ends up in the stress loading zone or the stress shadow depends on its orientation relative to the rupture plane and to the regional stress field. The calculation is standard geophysics, and it can be done for any pair of events where the fault geometries are reasonably well characterized. The Coulomb stress transfer from the April 14th Walker Lane magnitude 5, 7 to the Paharnagat shear zone has not been published in peer-reviewed form as of this writing. But the rough geometry suggests that fault systems oriented in the northwest-southeast direction, consistent with the Paharnagat's structural orientation, would be candidates for stress loading from a Walker Lane right lateral rupture. If the calculation confirms that the Paharnagat received net positive Coulomb stress change from the Silver Springs event, the 14-day delay becomes physically motivated rather than coincidental. And if the Paharnagat in turn delivered positive Coulomb stress change to fault structures further to the southeast, structures that sit in the Eastern California shear zone corridor connecting Nevada to the Mojave, then the sequence has a direction and a continuation that the two documented events alone do not capture. This is not speculation dressed as science. This is a standard geophysical inference based on documented fault geometry, regional stress orientation, and the established mechanism of Coulomb stress transfer. It is a hypothesis that can be tested against the seismicity catalog as it accumulates over the coming months. What it is not is a prediction that a specific earthquake will strike a specific location on a specific date. That kind of prediction is beyond the current state of earthquake science and will likely remain so for the foreseeable future.
What it is, instead, is a probabilistic elevation. Set of fault structures that were already accumulating stress from the plate boundary have potentially received an additional increment of loading from the April 2025 sequence. Their probability of rupture in the near to medium term is not dramatically higher than it was before the background. Loading is far larger than any stress transfer from moderate events, but it is higher. And higher probability on fault structures in the stress corridor connecting central Nevada to the Las Vegas region is a fact worth understanding clearly. The Las Vegas Valley sits on thick deposits of unconsolidated sediment, alluvial fans, lakebed deposits, and desert fill that has accumulated in the valley over millions of years. This geology matters for understanding seismic risk, because unconsolidated sediment amplifies seismic shaking. When seismic waves pass from bedrock into soft sediment, their amplitude increases and their frequency content shifts toward the longer periods that are most damaging to buildings. The same earthquake that produces moderate shaking on bedrock can produce significantly more intense shaking on the sediment-filled valley floor. This amplification effect is well documented and well understood. It is incorporated into the seismic hazard maps that inform building codes for the Las Vegas region. What is less well incorporated because it is less well quantified is the potential for network-mediated stress transfer from the Walker Lane and Paharnagat system to deliver loading increments to the fault structures. Most directly relevant to Las Vegas Valley shaking, the Las Vegas Valley shear zone is a system of northwest-trending faults that run beneath and around the valley. It is not the most active fault system in the region. The Walker Lane carries far more strain. and even the Paranagat is more active in terms of instrumental seismicity. But the Las Vegas Valley Shear Zone is the fault system closest to the highest concentration of people and built infrastructure in the region. Vents on it, even moderate ones, would be felt strongly in the valley due to the sediment amplification effect. Larger events could cause significant damage to a building stock that, while reasonably modern, was not designed with a major nearby fault rupture as the primary design scenario. The seismic hazard assessment for the Las Vegas metropolitan area is not negligible. The current USGS probabilistic seismic hazard maps show meaningful probability of experiencing moderate to strong shaking over a 50-year horizon, but the hazard maps are based on individual fault sources treated as largely independent. They do not fully incorporate the network behavior, the potential for a Walker Lane event to advance loading on the Paranagat, which advances loading on the Eastern California shear zone structures, which advances loading on the fault systems most directly relevant to Las Vegas Valley ground motion. Incorporating that network behavior into hazard assessments is not a simple problem. It requires Coulomb stress modeling for multiple event scenarios, post-seismic relaxation calculations over multi-year timescales, and geodetic monitoring sensitive enough to detect strain accumulation changes that occur in response to regional stress redistributions. The data infrastructure for this exists in principle: the continuously operating GPS network in the western United States, the dense seismic monitoring maintained by the USGS and university partners, the NSAR satellite coverage that measures ground deformation from orbit. What is less clear is whether the analytical framework being applied to that data in real time is sophisticated enough to detect network-mediated stress migration before it becomes obvious in the seismicity catalog. There is a monitoring station in the Las Vegas Valley operated as part of the Southern Nevada Seismic Network, a regional monitoring array that tracks seismicity in the area and feeds data into the national catalog. The station coverage in the region is adequate for detecting moderate events, but is not dense enough to provide the high-resolution picture of microseismicity that would allow detailed tracking of stress migration through the near-surface fault network. Improving that coverage would not predict the next earthquake, but it would give scientists a cleaner signal to work with when trying to distinguish stress migration patterns from background noise. The depth of the April 29th Paranagat earthquake carries information relevant to this discussion. The USGS final depth estimate placed the event at approximately 13.6 kilometers. Mid-crustal depth for the basin and range province. Some preliminary analyses suggested depths as shallow as 6.5 kilometers. The difference matters because it affects the geometry of stress transfer to adjacent fault structures. A shallower event generates a stress perturbation that is more concentrated in the upper crust, closer to the depth range where most seismogenic faulting occurs, and more relevant to the loading state of the faults most important for surface hazard. A deeper event generates a stress perturbation that is more diffuse at the relevant depths, until the depth is better constrained through waveform analysis, through the distribution of aftershocks if they are detectable, through geodetic modeling of the surface deformation field. The geometry of the stress transfer calculation carries corresponding uncertainty. This is the kind of uncertainty that geophysical monitoring is designed to reduce but cannot eliminate entirely for moderate events in regions of imperfect station coverage. It is also exactly the kind of uncertainty that matters when you are trying to determine whether a stress redistribution pulse is heading toward a populated region on a timescale relevant to planning. What the seismicity catalog shows in the period following the 2 April events is worth examining carefully. In the first 2 weeks after the Paranagat magnitude for 7, the region produced a small but detectable cluster of magnitude 2 to 3 events distributed across the Paranagat fault system and its immediate vicinity, consistent with a normal aftershock sequence decaying according to the standard statistical patterns. No individual event in that cluster was newsworthy. Collectively, they confirm that the Paranagat system is responding to the main shock in the expected way. More interesting is whether the seismicity in the broader region, not just the immediate Paranagat aftershock zone, but the fault structures in the corridor between the Paranagat and the Las Vegas Valley, shows any departure from background rates in the months following the April sequence. That question cannot be answered definitively from the catalog available at the time of this writing. It requires several more months of data and careful statistical analysis to distinguish genuine rate changes from normal background fluctuation. But the question is the right one to ask. And asking it requires understanding what background looks like for this region and what a departure from background would look like. The seismicity rate in the southern Great Basin south of the Piranha Ghat and north of the Las Vegas Valley is low. This is not a region that produces frequent felt earthquakes under normal conditions. The fault structures in this corridor, including the California Wash Fault Zone and related structures in Clark County, Nevada, are real and mappable, but produce relatively little instrumental seismicity compared to the more active systems to the north. Low background seismicity makes departures from background easier to detect statistically, because the signal-to-noise ratio is better when the noise is low. It also means that even a modest increase in event rate, if it is spatially coherent and directionally consistent with stress migration from the north, would carry real information about the stress state of the corridor. The Clark County Fault System, the collection of fault structures immediately adjacent to and beneath the Las Vegas Valley, has not produced a significant earthquake in the modern instrumental era. That is important context. It is not evidence that the system is incapable of producing one. The paleoseismic record, the evidence of past earthquakes written in fault trenches and displaced geological features, indicates that the valley's fault structures have ruptured in the past at magnitudes that would be considered significant regional events. The timing of those past events is uncertain. The recurrence intervals are poorly constrained. What the record shows clearly is that the capacity exists and has been expressed before. There are roughly 2.5 million people in the Las Vegas metropolitan area, making it one of the larger population centers in the western United States. The economy is heavily concentrated in the hospitality and entertainment sector, an industry whose physical infrastructure includes many large buildings, tall towers, and densely occupied spaces that would be significantly affected by strong shaking. The Las Vegas Strip alone represents hundreds of billions of dollars of concentrated infrastructure, much of it high-rise, much of it on valley sediment, within the amplification zone that would respond most strongly to ground motion from the nearby fault structures. The building code history of the region is relevant here. Las Vegas grew explosively during the mid to late 20th century, a period when seismic design codes were less stringent than they became after major urban earthquakes elsewhere, demonstrated the cost of inadequate attention to ground motion design. The building stock includes a substantial fraction of structures built to older standards that would perform less well in strong shaking than structures built to current codes. Retrofit programs exist but are not comprehensive. The newer towers on the Strip are generally better designed than the older building stock in residential and commercial areas away from the primary tourist corridor. None of this means a catastrophic earthquake is imminent. The probability of a major rupture on the Las Vegas Valley fault structures in any given year is low by any reasonable estimate. But low annual probability compounded over decades becomes non-trivial probability over longer horizons. The question raised by the April 2025 sequence is whether the network behavior of the Walker, Villain, and Piranha Ghat system has incrementally advanced the loading on those structures in a way that should be reflected in updated hazard assessments.
The honest answer is, we do not know yet. The Coulomb stress transfer calculations have not been done and published. The post-seismic relaxation models have not been run for this event pair. The geodetic data from the GPS network in the region has not been analyzed for anomalous strain signals in the aftermath of the April sequence. These are things that need to happen, and they need to happen with the urgency appropriate to a question that has 5 million people at one end of it. There is a pattern recognition challenge embedded in this situation that is worth naming directly. Human beings are good at recognizing patterns that express themselves on timescales we can observe within a single lifetime: days, months, years. We are much less good at recognizing patterns that express themselves on timescales of decades because the human attention span is not calibrated to decades. Each event in a decadal sequence looks, at the time it occurs, like an isolated event. It gets covered as an isolated event. It fades from public attention as an isolated event. The pattern it is part of only becomes visible in retrospect, when researchers pull up the full catalog and see what no single event announcement could show. The Central Nevada Seismic Belt sequence of 1915 to 1954 is the most instructive example available for the current situation. 4 major earthquakes across 4 decades, each one the next segment of the same regional system, each one legible as part of a sequence only after all four had occurred. The researchers who wrote the first papers connecting them into a sequence did not have the benefit of real-time network monitoring, continuous GPS deformation data, or INSAR satellite coverage. They had seismograph records and field mapping, and the accumulated wisdom of decades of observing how fault systems behave. We have all of those tools now and more. The question is whether we are using them to ask the right questions in real time, while the sequence is happening, not after it has completed, and whether the answers those tools can provide are being communicated to the people who need to act on them. The seismographs are recording. The GPS receivers are measuring millimeters of crustal motion across the entire region, updated continuously. The INSAR satellites are making passes every 12 days, comparing radar images of the Nevada and California desert to detect surface deformation that the human eye cannot see. The data is arriving. The catalog is growing. The stress field is evolving in the crust right now in ways that will eventually be legible in the seismicity record. What the April 2025 sequence has done is open a window, a period during which the monitoring data is most informative about the state of stress in the network, and during which the analysis being done on that data can either detect or miss the early signals of where the stress is going. That window does not stay open indefinitely. The post-seismic adjustments decay. The geodetic signal from the April events fades back toward the background noise floor. The catalog begins to look like background seismicity again until the next event provides another window. 14 days separated the Walker Lane event from the Pahranagat response. We do not know what the interval will be between the Pahranagat event and whatever comes next in this corridor. We do not know whether anything comes next on a time scale relevant to human planning. The central Nevada seismic belt took 40 years to express its full sequence. The interval between events in a network sequence is not predictable from the individual events themselves. What is predictable, or at least what is tractable, calculable, and not beyond the current state of the science, is the geometry of the stress transfer. Which fault structures received net positive Coulomb stress from the April events? How large that stress increment is relative to typical background loading rates? How long it would take, at typical background loading rates, for a fault that received that increment to approach its own failure threshold? These calculations do not produce a date, but they produce a probability distribution, a sharper, more informed picture of the hazard landscape than the one that existed before April 14th. That sharper picture needs to be drawn. It needs to be communicated to the people responsible for building codes, emergency planning, and public communication in the Las Vegas metropolitan area. And it needs to be drawn now, while the window is open and the data is fresh, not after the next event in the sequence makes the question urgent in ways that no longer permit careful analysis. 2.5 million people live at the end of this stress corridor. They are not thinking about the Pahranagat shear zone. They are not thinking about the Walker Lane. They are not thinking about the central Nevada seismic belt sequence of 1915 to 1954, or what it might mean for the fault structures beneath the valley where they live and work. That is not their job. Their job is to live their lives in reasonable confidence that the systems responsible for understanding and communicating seismic risk are doing that job well. The April 2025 sequence is a test of whether those systems are working. Not a catastrophic test. No one was hurt, nothing was destroyed. The sequence so far has been well within the range of normal regional seismicity. But a diagnostic test. A moment when the data infrastructure, the analytical frameworks, and the communication channels between geophysical monitoring and public risk awareness are all being asked to do what they were built for. The earthquakes are in the catalog. The direction is in the geometry. The question of whether this sequence is the opening of something longer or an isolated pair of events that resolves quietly is being answered right now in the crust. In the language of stress and strain that the Nevada desert has been speaking since long before there was anyone here to listen. 2.5 million people are at one end of the corridor. The stress redistribution from the April sequence is at the other. The distance between them, measured in fault lengths and stress transfer pathways and the slow mechanics of post-seismic relaxation, is not as large as the map makes it look. The seismographs know this. The GPS receivers know this. The question is whether we are paying enough attention to hear what they are saying, before the answer arrives in a form that requires no interpretation at all. There is a concept in seismology called seismicity migration, and it is worth understanding precisely because it is the technical description of what the title of this piece is claiming. Seismicity migration refers to the spatial movement of earthquake activity over time, a pattern in which the locus of seismicity shifts progressively from one location to another in a way that is not random but directional, following the pathways through which stress moves in the crust. Migration can happen through several mechanisms. Fluid migration, the movement of pressurized water through the porous rock of the crust, can trigger seismicity along its pathway as it elevates pore pressure on fault surfaces it passes through. This mechanism is well documented in induced seismicity from wastewater injection and in natural settings near volcanic and hydrothermal systems. It is relatively slow, typically moving at speeds of kilometers per day to kilometers per month. Stress migration through Coulomb transfer is faster, essentially instantaneous for the static component, with the post-seismic component evolving over weeks to months. When a fault ruptures, the stress redistribution propagates outward at seismic wave speeds, which means the static stress field is updated everywhere simultaneously. But which faults respond, and when, depends on how close each fault was to its own failure threshold when the stress increment arrived. Faults that are already highly loaded respond quickly. Faults that are further from failure may not respond for months, years, or decades. The apparent migration of seismicity, the pattern in which earthquakes seem to move through a region over time, often reflects this combination. The stress redistribution arrives everywhere essentially simultaneously, but the responses are staggered by the varying proximity to failure of different fault segments. What looks like migration in the catalog is often really the progressive revelation of which faults were closest to failure at the time of the triggering event, expressed in the order in which they cross their failure thresholds. In the April 2025 Nevada sequence, the apparent migration direction, north to south from the Walker Lane toward the Pahranagat, and potentially toward the Eastern California shear zone corridor, is consistent with the regional stress field orientation and the geometry of the fault systems involved. A right lateral rupture on a northwest trending Walker Lane fault would preferentially load other northwest trending right lateral faults to the southeast. Along the structural corridor connecting Walker Lane to the Eastern California shear zone through the Pahranagat relay. This is not a controversial geophysical claim. It follows directly from the standard Coulomb stress analysis framework that has been applied to hundreds of earthquake sequences worldwide. The controversy, if there is one, is about whether the stress increment from a magnitude 5.7 is large enough and the receiving faults close enough to failure to produce observable responses on human timescales. That is a quantitative question with a quantitative answer that requires the actual stress calculation to determine. Without that calculation, the argument rests on the pattern, two events 2 weeks apart, in the right structural positions, at the right separation distance, with timing consistent with post-seismic stress evolution. That is circumstantial evidence for stress-mediated connection, not proof. But circumstantial evidence in geophysics, when it is geometrically motivated and temporally consistent with known mechanisms, is the starting point for the kind of analysis that can sharpen it into something stronger. The Las Vegas Valley is separated from the Pahranagat shear zone by approximately 250 kilometers of desert. That is a long distance for stress transfer from a magnitude 4.7 earthquake. The static stress change from a magnitude 4.7 at that distance is extremely small, far smaller than typical earthquake stress drops and far smaller than the stress accumulation rates on faults in that region from the ongoing plate boundary loading. A single magnitude 4.7 in isolation does not meaningfully change the hazard picture for the Las Vegas Valley. But the April 2025 sequence is not a single magnitude 4.7 in isolation. It is a magnitude 5.7 followed by a magnitude 4.7, both in the fault corridor that connects the Walker Lane to the structural neighborhood of Las Vegas. The stress change from the magnitude 5.7 is larger and extends to greater distances. The cumulative stress change from both events together is larger still. and both events occurred in a region that is already delivering a background loading rate to the fault structures of the southern Great Basin from the ongoing plate boundary motion. The hazard question is not whether the April events were large enough to trigger an earthquake in Las Vegas tomorrow. They were not and almost certainly did not. The hazard question is whether the combined effect of the April sequence on the stress state of the fault corridor between the Pahranagat and the Las Vegas Valley is large enough to matter when integrated over the multi-year to decadal timescales on which seismic hazard is assessed. To answer that question, you need the Coulomb stress models, you need the post-seismic relaxation calculations, you need the geodetic data showing whether the GPS stations in the corridor recorded any anomalous strain signals in the aftermath of the April events. You need the detailed microseismicity catalog for the region between the Pahranagat and Las Vegas Valley, analyzed for rate changes that exceed statistical background fluctuation. This work is tractable. It is within the capability of the monitoring and modeling infrastructure that already exists. The question is whether it is being done, and whether the results, when they exist, will reach the people who need to act on them. There is a communication gap in earthquake science that is worth naming, because it contributes directly to the situation this article is trying to describe. The people who do the science, the seismologists, the geodesists, the Coulomb stress modelers, produce results that are published in technical journals, presented at professional conferences, and discussed within a community that has the mathematical background to evaluate them. The people who need to act on those results, the city planners, the building inspectors, the emergency management directors, the elected officials responsible for the safety of the people in their jurisdictions, often do not have that background and do not have direct access to those results in a form they can readily use. The gap between what the science knows and what the public and its decision-makers understand is not primarily a gap in information availability. The USGS publishes its hazard maps. The earthquake catalogs are publicly accessible. The peer-reviewed literature is findable. The gap is in translation, in the process of converting technical scientific results into actionable guidance for non-technical decision-makers on timescales relevant to the decisions they need to make. This article is one attempt at that translation. It is not a substitute for the Coulomb stress calculations. It is not a substitute for the geodetic analysis or the detailed microseismicity study. It is a description of the question that those analyses need to answer, and an argument for why the answer matters for 5 million people who are currently not being asked to think about it. The building codes in the Las Vegas metropolitan area are based on probabilistic seismic hazard assessments that are updated periodically as new data and new science become available. The most recent significant update incorporated improved fault models and updated GPS-based strain rate estimates. What it did not incorporate, because the science was not yet available, was a network-level model of Coulomb stress interaction between the Walker Lane, Pahranagat, and Eastern California shear zone fault systems and its implications for the loading state of the Las Vegas Valley fault structures. That network-level model is now more motivated than it was before April 14, 2025. The April sequence is not the reason to build such a model. The structural geometry alone was motivation enough. But the April sequence is a reminder that the network is active, that the stress is moving, and that the corridor connecting the Walker Lane to Las Vegas is not a geological abstraction. There are things that residents, planners, and officials in the Las Vegas metropolitan area can do with this information even without waiting for the full scientific analysis. The most important is not a specific action, it is a reframing. The mental model of seismic risk in Las Vegas needs to update. The relevant risk is not limited to the well-known California fault systems. It includes the Walker Lane, the Pahranagat shear zone, the Eastern California shear zone, and the fault structures within and adjacent to the Las Vegas Valley itself. These are not hypothetical. They are mapped, they are monitored, they have produced earthquakes in the past, and the April 2025 sequence is a reminder that the network connecting them is active. That reframing matters for building retrofit prioritization. It matters for emergency planning exercises. It matters for the public communication that shapes whether residents have realistic expectations about seismic risk. Expectations that, when calibrated correctly, tend to produce better preparation and less panic than either false reassurance or alarmism. The scenario that seismic hazard analysts worry about for the Las Vegas region is not a repeat of the central Nevada seismic belt sequence at the same magnitudes. A magnitude 7 rupture on a fault directly beneath the Las Vegas Valley, while not impossible in the very long term, is not the most likely near-term scenario given the current strain rates and fault geometries. The scenario that the monitoring data and the April 2025 sequence are most relevant to is the intermediate one. A magnitude 5 to 6. 5 event on a fault structure in the corridor between the Pahranagat and the valley, close enough that its shaking would be amplified by the valley sediments and felt strongly throughout the metropolitan area. That scenario does not require the April sequence to have dramatically changed anything. It requires only that the fault structures in that corridor, already loading from the plate boundary, continue to do what fault structures do. The April sequence is relevant because it potentially advanced that loading. It is not relevant because it made something that was previously impossible suddenly possible. The fault structures in the corridor are real. The loading is real. The exposure, too. 5 million people, concentrated infrastructure, a building stock with significant older inventory, is real. The question of whether the April sequence measurably advanced the timeline for events in that corridor is the question that the science needs to answer. The earthquakes that have already occurred are in the catalog. The stress they transferred is in the crust. The monitoring infrastructure is recording. The window during which that data is most informative about the state of the network is open now and will not remain open indefinitely. 2.5 million people live at the end of this corridor. The sequence began 400 kilometers to the north. The direction of travel is geometrically motivated, historically precedented, and currently unresolved. The data is arriving. The clock is running. And somewhere between the Pahranagat shear zone and the Las Vegas Valley, in fault structures that have not spoken loudly in the modern instrumental era, the stress that the April sequence delivered is sitting in the rock, waiting for the conditions that will determine when and how and at what magnitude it eventually speaks. The seismographs are listening. The question is whether we are. The answer to that question will not be found in the earthquake catalog. It will be found in the decisions made by the people responsible for seismic risk management in the Las Vegas metropolitan area over the next several years. Do they commission the Coulomb stress analysis that would sharpen the probabilistic picture? Do they update their emergency planning scenarios to include events in the fault corridor north of the valley? Do they communicate the reframed risk picture to the public in a way that supports better preparation without generating unproductive alarm? These are not technical questions. They are governance questions. And governance questions about low probability, high consequence hazards are notoriously difficult to answer well because the incentive structures around them are badly aligned. The cost of preparation is immediate and certain. The benefit of preparation accrues only if the hazard materializes, and if it does not materialize within a political or administrative cycle, the preparation looks like waste. Every major urban earthquake in the last half-century, Northridge, Kobe, Christchurch, L'Aquila, has been followed by an inquiry that identified in retrospect warning signs that were present and available, but not acted upon. The warning signs were not hidden. The science was not suppressed. The monitoring data was being collected. What failed was the translation of that data into action on timescales relevant to prevention rather than response. The April 2025 Nevada sequence is not a warning sign of an imminent catastrophic earthquake in Las Vegas. To say otherwise would be to overclaim what the data supports. But it is a reminder that the fault network connecting the Walker Lane to the Las Vegas Valley is active, that stress is moving through it in a geometrically motivated direction, and that the monitoring infrastructure and analytical tools to characterize that movement exist and are available. Using them well, asking the right questions of the right data on the right timescale, is the difference between understanding the risk clearly enough to prepare and understanding it only clearly enough to respond. 2.5 million people live at the end of the corridor. The stress redistribution from April is in the crust. The window to analyze it carefully is shorter than it looks. The seismographs are recording. Everything depends on whether we are paying attention to what they are saying. Not after the next event makes the question urgent, but now, while the data is fresh and the analysis is still possible, and the answer can still shape what we do before the ground makes its next move. The fisherman in Pozzuoli noticed his boat was at the wrong angle and said nothing because there was nothing obvious to say. The residents of Pleasant Valley, Nevada in 1915 felt the ground open beneath them and rebuilt because there was nothing else to do. The people of Dixie Valley felt it again in 1954 and understood eventually that the sequence they had lived through was a single event spread across 4 decades. Understanding that now, before the next event, not after, is the only form of preparation that matters at the scale of a city. The geology does not announce itself. The stress does not wait for an audience. The 2.5 million people at the end of this corridor deserve decision-makers who are paying attention to what the instruments are saying, while there is still time to act on it. The earthquakes are migrating. The direction is clear. The question is not whether the science can see it. The question is whether the people responsible for those 5 million lives are looking